Alright, nuclear chemistry is the lesson today. The rest of the chemistry course, the entire thing, is all about interactions between stable atoms. Now, this is the one topic here, nuclear chemistry, where we're going to talk about unstable atoms and what happens when you have an unstable atom. So, to clarify, the vast majority of the atoms we see around us are stable. Almost everything you deal with is stable unless it's specifically a nuclear atom, or one that's used in nuclear chemistry. You won't often just come across an unstable atom. So when we say it's stable, what we're saying is that the nucleus retains the same number of protons and neutrons pretty much indefinitely, and so therefore the chemical properties of the element are unchanged. Now let's talk about this neutrons and protons concept. Basically, at the core of every atom is a certain number of protons, and for almost every atom, except one that we'll deal with shortly, a certain number of neutrons as well. So you'll remember that the basic concept is that we've got let's call that a proton I've just drawn and a neutron, and these are basically just a these are all in a ball, mixed together. Try and get the same color. Failed. Anyway, if you can imagine a ball of protons and neutrons, and then around that the electrons kind of fly around, doing their thing, their different orbits. It's not really. So that's the standard model of a nucleus in here and an atom as a whole out around. Now, what we're saying is that some configurations, some combinations of protons and neutrons are stable and some aren't stable. And we're not going to get into exactly why it is that some are stable and some aren't, but it is important that some are and some aren't. And the basic rule of thumb of it is that for light elements, the ratio of protons to neutrons is 1 to 1, and for heavy, the ratio is 1 to 1.5. So, yeah, so that's protons, it's neutrons. So, basically there is a kind of stable ratio that creates a stable nucleus for most elements, and these are those ratios. So for the lighter ones it's 1 to 1. As they get heavier it's more like 1 to 1.5, and if it deviates from this then it starts to be unstable. Now when we talk about a deviation in this context, we're talking about an atom that has a certain number of protons, present them in green, and a certain number of neutrons that isn't standard. Now, what we're talking about then are different isotopes of a given element. So the way it works is this. For a given number of protons, that atom will always be the corresponding, I don't know how to visually represent this, but the corresponding element. So it's the number of protons that determine what element you are. So if you've got one proton, you're a hydrogen. If you've got, I believe it's 7, yeah, I believe 7 protons, then you're an oxygen. So it's the number of protons that determine what element you are. If we change the number of neutrons in an element, then we've got a new isotope of that same element. So if we change the number of neutrons in a nucleus, rather than changing an element, you've still got the same element, but now you've got a new isotope of that element. So when we're describing things in nuclear chemistry, we're always going to refer to what isotope it is. So you might see something like molybdenum 99 or MO 99 up here. So it's in this part of chemistry that we're going to start referring to the atomic weight of the element in question. So let's look at some simple examples of isotopes and what the nomenclature means and this kind of stuff. Okay, so the most standard isotope of hydrogen is hydrogen 1. What does this mean? Well, it means that the element is hydrogen, so it has atomic number 1, but it's also got, and this is what this refers to, it's also got an atomic weight of 1. So how can you have atomic weight number 1 and atomic weight of 1? Well, just very quickly, atomic number is the number of protons, so it's got 1 proton, and its total weight, so that 1, its total weight is 1, which means that it's got nothing extra, so it's got 0 neutrons. Maybe I'll fill in these protons. Sure. So it's got 1 proton at 0 neutrons for a total weight of 1. But this is not the only form of hydrogen that's out there. There's also hydrogen 2, which is commonly known as deuterium. Okay, so what's deuterium? Well, it's got atomic number 1, it's still hydrogen, so we know it's got 1 proton, but it's also got 1 neutron to bring it up to atomic weight 2. So it's got a proton of 1, proton count of 1, but it's got a neutron count 1 as well to add up to 2. So it's a hydrogen nucleus because it's got 1 proton, but it's also got a neutron in there, giving it a weight of 2. Now, you remember that the stable ratio for protons to neutrons is 1 to 1. H1 gets away with it. It is stable even though it doesn't have that ratio. But this deuterium is quite stable as well because it's got the right ratio. But there's another isotope of hydrogen out there, and it's known as tritium. And as the name suggests, it's got atomic weight of 3. It's H3. So once again, 1 proton, because it's still hydrogen. But 2 neutrons. So its total atomic weight is 3. It's just 2 plus 1. So yeah. Now, because it's heavier than it should be, basically, we really just cannot go into the complicated reasons why this is the case. But tritium is an unstable element. So what that means is that it's subject to nuclear decay. And what that means is that sooner or later, that nuclear core, which is not stable and is subject to decay, it's going to break apart. And when it does so, it can release certain sorts of energy. We'll come back to exactly come back to exactly what energy and what kind of emissions that tritium will give out a little bit. So we're going to go on to nuclear decay, but I'll just break the video there. And yeah, so the next video will begin with nuclear decay, alpha, beta, and gamma decay.